So welcome back again.
Sir,
So
we are
if
recording.
I'm recording. The recording switch is going to display after a while. Okay, so if you recall, in our last class, we did what? Functions of several variables. Okay. So specifically, we consider a function of two variables like this. Function of two variables like this. Okay. And we were talking about, domain and range of such functions of two variables. Okay. So today we are going to emphasize more on the visualization of the function of two variables. Okay. So then, if time permits, then we'll try to reach function of three variables, and for that matter, we can extend it up to functions of more than three variables, like say n variables, right? Where your domain will be a subset of Rn. Okay, fine. So let us try to this graph of a function of two variables. Okay, graph of a function of two variables. Okay, fine. See, if you recall, suppose from your NA 101 single variable calculus course, so suppose I consider a function of a single variable, say x. So then, if I want to plot this, the graph of the function in two-dimensional plane, so then you see that it is nothing but a curve. It is nothing but a curve. It is something like this. It is something like this. So basically, in this particular case, the your graph of f, if I denote it by gf, so it is nothing but, and let us assume that for this function f, the domain is some interval, say a b, maybe. Sorry, domain is some interval, your a b here. Okay. So then the graph is going to consist of points like xy belonging to R2, such that your y equal to f of x, where x belongs to that interval a b. Right? We would have written it something like this. Is it okay? Fine. So similarly, suppose I consider a function of two variables from a domain D, which is a subset of R2, right? 2 is set of real numbers. Okay. So then what I'm going to do, then the graph of f, it is going to be something like, say here, the graph of f, it consists of points in R2, right? So these being a function of two variables, your graph is going to consist of points in R3, okay, such that your j equal to f of xy, and this xy belongs to this domain of definition, this. Okay, so basically you can see that now if I want to visualize the graph of a function of two variables, then you will see that you have to visualize some points in R3. That means you have to visualize some points in space, right? The set of all those points, if you take a union, in fact, what you are going to get something like a surface. Okay, so I am going to draw it, and after that I am going to show it to you in slides so that it is easier for you to visualize and understand. Okay, fine. So how we can visualize it? Say okay. Say suppose this is my This is my domain of definition of a function of two variables. Function of two variables. Okay, and let me call it as D. Okay, so then for each point belonging to this domain of definition, what I can do, I can plot. I can take that. I mean, if J is equal to f of xy, so then what is going to happen? I am going to get J in such a way that it is at a height J from the xy plane, right? So corresponding to this point, I am going to get a point xyz here in space such that Z equal to f of xy, right? So similarly, if I try to find all those points corresponding to the points belonging to D, so then what I am going to get, it is going to generate a surface like this. It is going to generate a surface like this, isn't it? It is going to generate a surface like this. Fine. Okay. So this surface is going to be visually the graph of the function f. Is it okay? And again, please remember that here I mean intentionally. Intentionally, I have drawn it like something in the, first octet. It is not necessarily like that. Okay, it is not necessarily like that. So the way I have drawn the function in such a way that your J is always going to be positive. It is not necessarily so. Okay, so you may get some surface like say you may get some surface like this. You may get some surface like this. Okay, which may look like this. Some portion is going to be below xy plane. Some portions are going to be below. Above xy plane. Okay, so it may contain both positive and negative values. Okay, fine. So now just let me show you a better picture in the slides. So this is about graph. So another way of visualizing the behavior of a function of two variables is to consider its graph. So I have already defined it. So it is going to look like this. Say suppose if you your domain is here in the xy plane, right? It is the kind of this brownish shaded region. So you know that if you consider any point as a three-dimensional point here on xy plane, so its coordinates are going to be x, y, 0, and then you are going to get the image of this point in terms of the function f of xy. So this height is going to be f of xy, and corresponding to this, I am going to get a point xy, f of xy. And if I take the image of all those points like this here, it is going to generate a surface S. Okay, fine. So this is about the graph of the function. So now let us try to sketch some graph of a function. Okay, and from my second example that I'm about to do. So I'm going to make some more comments on that. Say 6 minus 3x. Okay. Say suppose I'm considering this function. I want you to sketch this graph of this function. Okay. So can you tell me how to go about it? See, the first thing that we are going to do, we are going to assume that J equal to f of xy, because I am going to designate the third coordinate along the z axis. Okay, fine. So if this is so, from here you can see that this can be converted into something like 2x plus 3y plus z equal to 6. Okay, fine. And then if this plane, this is nothing but a plane in 3D. We have already done the equation of a plane in the vector form, which later on it can be extended into something like this. So let me tell you, this can be converted into something like in this form: x by a plus y by b plus z by c equal to 1. So if you can convert it into this form, let me guarantee you that you can read it on your own. So then this is going to represent a plane in space such that it intercepts a unit from x axis, b unit from y axis, and c unit from z axis. So likewise, if I do it here, if I divide throughout by 6, I'm going to get x by 3 plus y by 2 plus z by 6 equal to 1. Okay, so now if I want to draw the graph of the function, so then what is going to happen if say this is, let me make it smaller, 1 2 3, suppose this is 3 and suppose this is 2 and j 1 2 3 4 5 6, this is 6. So then what is going to happen? Okay, so this plane is going to be the graph of my function f of x, right? Given by this. Is it okay?
Yes.
Yes, sir.
Right? Okay. So now let us take another example. I mean g of x, right? So suppose this example we had already taken earlier in order to find the domain and range of this function. Okay. So as before, I mean what we are going to do, I am going to assume that z equal to this. Okay. And from here, eventually we are going to get x squared plus y squared plus z squared equal to 9. Is it okay? And you know that this is nothing but the equation of a what?
Sphere.
Equation of a sphere. So now, suppose this is the sphere. Suppose this is the sphere. Your x squared plus y squared plus z squared equal to 9. Okay? Say x, y, z. Say suppose this is the sphere x squared plus y squared plus z squared equal to 9. But if I take the sphere in this way, then you will see that if I take any point here in the xy plane, so then corresponding to this point, what is going to happen? I am going to have two values of z, isn't it? And that violates the definition of a function, isn't it? Right?
Yes.
Because to each point belonging to domain of definition of a function, I should get a unique point. What? In the range of the function.
Range.
Isn't it? So that is why, and you will see that the original function, because given only in terms of positive square root of 9 minus x squared minus y squared. So in order to define a function, what you must have, you must consider either the upper hemisphere, okay, upper hemisphere of this sphere, okay, or the lower hemisphere. Is it okay? Fine. So this is going to give you some idea. Yes, this is going to give you some idea about the graph of a function. It is going to give you an idea about the graph of a function. For example, that we have taken. So this is the graph of the function given by 9 minus x square root 9 minus x square minus y square. So similarly, if I had it minus square root of 9 minus x square minus y square, I would have taken the lower hemisphere. That's it. And again, now you have seen that, like say a function of two variables can be visualized as surfaces. The graph of a function of two variables can be visualized as surfaces. So in my next slide, what I'm going to do, I'm going to show you some functions and their graphs as surfaces. So it is something like this. Okay. And one thing I would like to tell you is that whenever you have something like e to the power, I mean x squared, y squared, something like that, x squared plus y squared, x squared minus x squared minus y squared, something like that, you should always remember that you are going to get some bell-shaped surface. Okay, whenever you have something like e to the power minus x squared, something like that, minus x squared minus y squared, you are always going to have something like some bell-shaped surface. Okay, so now next thing what I'm going to do, I'm going to come to the concept of level curves. Okay, I'm going to come to the concept of level curves. So let's see what are level curves. Okay, so now what is happening? I mean, level curve. Let me try to give you I will try to explain it to you with some practical examples. See, I mean, like say India is a vast country. I mean, while some part of India it is drilling under extreme heat, some part of it may be, I mean, like say it may be extremely cold, something like that. Okay, so a measure of, I mean, which part of India is cold and which part of India is hot, I mean, that we can find out from the isotherms. You know that isotherms are nothing but what? Some lines, some continuous lines, okay? I mean, and then those lines, what they do, they signify equal temperature. So now, say, suppose if say this is the rough map of India. This is the rough map of India. Say here is northeast, and this is the northern part, and this is the I mean western part, and this is the southern part. Okay. So now, if I consider this India along XY plane, so then what is going to happen? Now, if I consider it along say XY plane, so now if this is my domain of definition, of a function, and if I consider temperature to be a function of x and y, the coordinates in this plane. So then what is going to happen? So then it is going to generate some surface. Here. Okay. So for example, I'll come back to this later on. For example, let me tell you is that if you take say j equal to x squared plus y squared. So this is okay. What is this going to be? The graph of the function j equal to x squared plus y squared.
It's like cone. Cone.
Now. Paraboloid, yes. It is going to be paraboloid. Okay. Cone will be j equal to this. It will be above, and if this is minus, this will be below xy. Okay. So this is nothing but this surface. This is nothing but the surface j equal to x squared plus y squared. Okay. So now, what we are going to do, we are going to intersect this surface with a plane parallel to xy plane. Okay. Say suppose I want to cut this with a plane parallel to xy plane, and it is given by say j equal to k. Okay. So then what it is going to do? This plane is going to cut this surface this surface into a circle, isn't it? Right?
Yes.
Right? Because this height is k, this height is k. So this circle will be given by x squared plus y squared equal to k. Right? Now what I can do, I can take the projection of this circle here. I can take the projection of this circle here on the xy plane. Okay, on the xy plane. So this circle is going to be nothing but this. Is it okay? Fine. So similarly, if I take this at a different height, say k1 greater than k. So if I take another plane k equal to k1. So then if I do the same procedure, so then I am going to get even a bigger circle, right? X squared plus y squared equal to k1. Is it okay? Fine.
Yes.
So what are level curves? What are level curves? Okay, level curves are nothing but curves in the xy plane which has been obtained by considering a function f of xy and considering the equation f of x comma y equal to k, when k is a constant. But another important thing here, that this k, it must be in the range of the function f. Range of the function f. Okay, I'm going to show you the formal definition in this slide. So they are called level curves, and if you consider the curves along the surface itself, these are called contour curves. Okay. So now, if I come back to this example, if I come back to this temperature example, suppose I draw the graph of the temperature function all over India, right? So then again, if I cut it which parallel lines parallel to xy plane. So then what it is going to do? They are going to generate some curves, isn't it? They are going to generate some curves, and along those curves, the temperatures are going to be equal, isn't it? So that is why they are nothing but isotherms. So you should remember that isotherms, they are also level curves. Okay. So what is the formal definition of level curve? So I'm going to show you one figure here. So then it will be more clear to you. Okay, suppose this is the graph of a function. Okay, this is the graph of a function. And so here also there's an example. So what it is being done? So it is an inverted, inverted paraboloid. Can you guess what is the equation of that paraboloid? See, whatever I have drawn in the blackboard, if you recall that. So if I instead of j equal to x squared plus y squared, if I had taken j equal to minus x squared minus y squared, I would have gotten inverted, inverted paraboloid, right? With vertex at 0, isn't it? Fine. So now this paraboloid is at a this paraboloid is at a height, some height above xy plane, isn't it? If this particular point, its value, say, suppose its value is say c, value of j at this particular point is c. So obviously the equation of this paraboloid is going to be c minus x squared minus y squared. Okay. So now here you can see that this blue plane, which is parallel to the xy plane, it is cutting this paraboloid and it's cutting it into a circle, right? And if you take the projection of the circle over xy plane, this circle is nothing but the level curve, and its equation is given by j equal to k. So if you take j to be equal to f of xy, so it is going to be given by f of xy equal to k. Fine. And see here also, it is kind of a mountain, okay, right? And then, I mean, like say if you take a ground level, so your k is going to be equal to 0, so that means j equal to 0 here. So you are going to get something like this. So this is the formal definition of level curves. The level curves of a function f of two variables are the curves which equations f of x comma y equal to k, where k is a constant in the range of f. That is very, very important. In the range of f, you cannot, like say, you cannot choose k beyond the range of f. You cannot choose k beyond the range of f. Is it okay? Fine. Because if you look at it, say suppose this at this particular point the height is suppose 450. So now if you take k to be equal to 500, you are not going to find a plan j equal to 500 which is going to be intersecting this surface, isn't it? Is it clear? Fine. If the peak point of the mountain is say at a height 450 feet, right? And if we consider a plane j equal to 500, then the j equal to 500 plane is never going to, cut this mountain, isn't it? So that is why this part is very important. In the range of f, it is very, very important. Okay. So now, what I'm going to do in my next slide, I'm going to show you some surface. I think four surfaces will come. And then I'm going to show some level curves, and those level curves are correspond to those surfaces, but they are not ordered. You have to tell me which one corresponds to what. See, I have some surfaces here, and I have some level curves here. So can you tell me which is related to which one? One or two will do. You can try the remaining at home. This should be easy. This E corresponds to what?
The third one.
Yes, E corresponds to the third one. Okay, and then any idea? Okay, this one should be easy. See, there is some bell set here and some bell set one above, one below. So this should correspond to what?
Fourth.
Is it fourth or something else? For me, it should be 5. And B should correspond to 6. You take it home. Okay. Can you match these surfaces and then level curves? You try it at home. Okay. And in Stewart's book, there are other examples as well. Okay, fine. So now I'll come to another interesting scenario here. See, so far what I have done, done today the graph of a function, okay, and how to visualize it. So you can visualize it as surfaces in 3D, right? And then what we did, we we define level curves. Okay, so you know that level curves, they are nothing but some curves in xy plane, and you know the methodology of finding out the level curves out of those graph of the function, which is a surface. So now, let me ask you this question. So suppose, I take the function f of x, y, z, and I am keeping it very simple. Say x squared plus y squared plus j squared, right? So now, obviously, you know that if I want to find out the graph of this function, so it is going to consist of, and of course, suppose I mean, xyj, belongs to some domain D in R3, right? So then it is going to be something like xyzu, right? Belonging to R4, right? Such that your xyz, belongs to D, and your f of xyz equal to u, right? And D, of course, this is a subset of R3, right? Fine. Earlier, what we did, for a function of two variables, I was taking the union of all those points like x, y, z in R3. So now, can you visualize these points in R4? Actually, right? It is very difficult. Is it okay? Fine.
Yes.
Right? So that is where now if I want to consider something like the level curves, but if I equate say f of xyj equal to say some constant, right? Constant. So then you know that this is going to represent a surface, isn't it? Then this is going to represent a surface, like say if I say that x squared plus y squared plus z squared equal to say 9, right? So then it is going to represent a sphere of radius 3. Is it okay? Fine.
Yes.
Right? So likewise, like level curves, so what we are going to do, so for a function of 3 variables, again, if I equate them to some constant, they are going to give me some surfaces, and those surfaces are going to be called level surfaces of those functions. And of course, again, those constants, they have to be in the range of the function that has been considered. Okay, so now I'm simply going to again show you the slide here. See, this is the thing. See, if you have functions of 3 or more variables, right? So then, it's very difficult to visualize a function f of 3 variables by its graph, since that would lie in a 4-dimensional space, as I have told you, R4. However, we do gain some insight into f by examining its level surfaces, which are the surfaces with equations f of x, y, z equal to k, where k is a constant. And if the point x, y, z moves along a level surface, the value of f of x, y, z remains fixed. So you can see here, for different values of k, you get different surfaces. Of course, for this particular case, they are nothing but spheres of different radii. Okay, fine. So that's about this function of several variables, 6 graphs, and level surfaces. So now let us come to the very important concept of limit and continuity, and I'm going to start with a function of 2 variables. So, firstly, let us come to limit. Okay. Again, we are going to consider a function of 2 variables. Okay, where D is a subset of R2. Okay, fine. And then I say that limit of the function f at xy as xy tends to AB, xy tends to AB, where AB is a fixed point in the domain of definition of f. I say that this limit is equal to L, I say that when I say that that giving some very small positive number epsilon greater than 0, however small, you can find some delta greater than 0, which is of course another very small number, such that your mod of this minus L it is less than epsilon. Your whenever here what happens? Less than delta. Okay? Okay, so let us try to understand it geometrically and then it will be more clear to you. Okay, fine. So what it is telling you? I try to give you two figures. I try to give you two figures. Okay, say okay, say suppose say this is my domain. Let me make it a bit bigger so that's easier for me to take those points. Suppose this is my domain. Okay, and I am considering limit of a function at some fixed points here. Say this is the point A. This is the point A. Okay, so then what does this tell you? If you consider this inequality, so x minus a whole square plus y minus b whole square, so this is less than delta square, right? So this is nothing but the interior of the circle centered at AB and radius delta, right? Okay, so I am going to call that as disk. You can write it like this also, d delta AB, right? So basically, what I am having, so this point is AB. This point is AB. I am having this circle. Okay. Now, what I must have for all the points belonging to this circle. Say, suppose I take a variable point xy here. What you must have, like say, if you consider, say, this is my z-axis, and if I take z to be equal to f of xy, so for all xy line here, what must happen? Like say, suppose I have something like f of xy. So then, how should I write this? Okay. Suppose this is L minus epsilon. This is L plus epsilon. So for all xy lying in this circle, okay, f of xy must lie in this interval. F of xy must lie in this interval. Is it okay?
Yes.
Fine. I still haven't wrote in, I mean, L, exactly L. I still haven't wrote in. Okay. So now, if I want to give you a more three-dimensional effect of this, so probably what I can do, say suppose this is your domain G. Suppose this is your domain G, and suppose this one is D delta AB. Fine, D delta AB. Oh, this one, okay, centered at AB and radius delta. All the interior points I am considering. So obviously, this is going to have some image here, okay, and that is nothing but it is going to be some surface. It is going to be some surface. So then, what must happen? The highest point and lowest point of the surface, they must be your L plus epsilon. They must be in the range of L plus epsilon and L minus epsilon and L plus epsilon. That is the case. Okay, I'm going to show you better pictures. Don't worry about it. In my slides, it is going to be like that. So this is the geometrical interpretation. Is it okay? Fine?
Yes.
Fine? Okay. So let us show you and let us show you. Okay. Now you may be thinking that why this limit is so important. Why this limit is so important? Okay. So I'll come back to those figures later on. Again, you see, I'm going to show you two tables here. Say, I'm considering a function f of xy given by this, and another one, g of xy given by this. Okay. And what I'm going to do, I'm seeing for corresponding values of x and y, I am tabulating the values of f of xy and g of xy. So these are the things. So then, here, what is happening here? Like say, if you go from, this -1 towards 0, and similarly +1 towards 0 for y, and similarly for x, and similarly for y you do the same thing. Here you will see the value of f of xy, it is kind of approaching the value of 1. Isn't it? You can see that 0.999 and 0.999, it is 1. Is it okay? Fine? Isn't it? But for this particular function, if you look at this table, then you can see that it is inconclusive. It is inconclusive. Somewhere you are getting value 1. Okay. Fine. And somewhere you are getting -1. Okay, fine. So nothing can be concluded from this table. Okay. So now that I have already defined the limit of a function, at a point AB. So here, if that point AB is say 0, 0, that is the origin. So from this table, it seems that the value of that limit is 1. Whereas here it is inconclusive, so that is why we say that it doesn't exist. Okay. So now what we do, as I have told you, so this notation is used to denote the limit of a function of two variables at the point AB as xy tending to 0. We say that the limit is L. Okay. And this is the definition. Let f be a function of two variables whose domain D includes points arbitrarily close to AB. Okay, then we say that the limit of f of xy as xy approaches AB is L, and we write it as this. And this is valid if for any number epsilon greater than 0, there is a corresponding number delta greater than 0, such that if xy belongs to D and this inequality is satisfied, okay, then mod of f of xy minus L must be strictly less than epsilon. And I had already given the geometrical interpretation. So it is something like this. It is something like this. Okay, fine. And if you recall, I mean, when I drew the figure, I was not even worried about where this L is. I simply drew the interval L minus epsilon, L plus epsilon. So what he's saying is that, like say in this circle, for all the interior points lying in this circle, what is happening? I mean, their image under the function f, it must lie in the interval L minus epsilon and L plus epsilon. That is the substituted definition. Okay, fine. So now there is one extremely important thing you have to consider here. Okay, whenever we consider limit of a function of two variables. Okay, fine. Say, when we consider a function of one variable, say, I say limit x tending to a for a function of one variable, say f of x. Say I say this is equal to L. Whenever I tell you that, say suppose this point is A, this point is A in the real axis. Okay, right? So then if I consider all those variable points x, so then x can approach A from right, right? So in that case, all the values of x, they are going to be greater than A, right? And x can approach A from left also. In those cases, all the values of x is going to be less than A. So that is what we do, A minus and A plus, right? Now, what is happening there? If the limit has to exist for a function of single variable, what we must have, that limit x tending to A plus, I mean of fx, it must be equal to limit x tending to A minus your f of x. Only then we say that the limit exists, right? Now, for a function of two variables also, it is going to be the same thing. Now, the difference is that for a function of one variable, how the point x approaches A, there is only one way. It can approach A only along a straight line. Is it okay? Fine. But when you consider a function of two variables, say suppose I am considering a fixed point AB, okay, and then like say if I take all the neighboring points of this AB, because generally what we do, we consider a very small circle of radius delta centered at AB, right? If I consider all the neighboring points here, say suppose this is a magnified version. So then these points, they can approach AB obviously through straight lines, but they can approach through curves also, isn't it? Through curves also. Is it okay?
Yes.
Right? So again, this straight line also can be considered as a curve. So that is why here it is important is that if say xy approaches AB along a curve say C1, and if this limit of the function fx, if xy approaches AB along C1, this is equal to L1, okay?
Fx
This is
y.
along f of xy, yes, thank you. Okay, L1, if this is through the curve C1. If xy approaches AB along C1, where C1 is a curve, equal to L1. And similarly, if along C2, if it is say L2, if L1 is not equal to L2, then we will definitely say that the limit doesn't exist. Is it okay? Fine. Here, so the independence of the paths must be maintained. So whatever paths you take in order for the variable point xy approaching AB, you must obtain the same limit. Only in that case, we say that the limit exists. Is it okay? Fine. For example, if you recall those two tables that I have shown, then for g of xy equal to x squared minus y squared. This, when we were trying to find out the limit of this function as xy were tending towards the origin, we didn't get a clear picture. There was some kind of inconclusiveness there. Okay, so why is that happening? So let us see why was that happening. Now, see here it is about your I mean the origin. It is about the origin because what I'm doing here, I am trying to make all the neighboring points of the origin reaching the origin. Okay. Okay. Say suppose I'm trying to reach the origin through a line along say y-axis, along y-axis. So in that case, what must happen? X equal to 0. Is it okay? Fine. If
Yes.
I would like to approach x equal to 0, 0, say along y-axis, along y-axis. So then this your x squared minus y squared, x squared plus y squared. So because x is equal to 0, so I can write that limit. I mean, x is already 0. I can simply write it as limit y 0, then minus y squared by y squared, and this is equal to minus 1, right? Similarly, I can make this xy approach the origin along x-axis also. In that case, your y is going to be 0, right? Limit xy tending to 0, 0, your along x-axis. So if you want to take it, fine. So this will be equal to simply limit x tends to 0, x squared by x squared. So this is equal to 1. So here you can see that through two different approaches, you got two different limits, right? So that is why, since these are not equal, so that is why the limit does not exist. Is it okay? See, it is not necessarily like that you have to do this exercise only like this. You could have taken something like, say, a straight line passing through the origin. So it will be y equal to mx, isn't it? Right? So then what I could have done, I could have taken this as limit xy tending to 0, 0 equals x squared minus y squared and x squared plus y squared. So this is equal to limit say along say y equal to mx, right? So then what is going to happen? X tends to 0. So then for y, I am simply going to replace it with fine. And then this would have given you 1 minus m squared divided by 1 plus m squared, isn't it? And for different values of m, you will get different values of that limit, isn't it? So for some y equal to m1x, this will be my straight line. For some y equal to m2x, this will be my straight line approach, right? So for all those different approaches for different values of this m, you are going to get different values of this limit, right? So that is why this limit doesn't exist. Now, one thing you have to remember is that whenever you see a problem where you have to show whether the limit exists or not. I mean, non-existence of limit is easier to do. Okay, non-existence of limit is easier to do because you have to just once prove that. I mean, limits through two different approaches. I mean, do not match. Okay, but if you have to prove that the limit exists, limit exists, and if limit exists, then definitely you have to give a number, right? You have to arrive at a number, and through infinite number of approaches, you should get the same number, right? And that is a Herculean task. So that is why, in order to prove that the limit exists, so you must go to the definition of the limit. So that epsilon delta approach you must take. So if you can prove it through that, then you are done. Okay. So what I'm going to do, I'm going to take a small example. I'm going to take a very small example where the limit is going to exist, and I'll show you how to go about that. Okay, so suppose I am considering this function. Okay, and suppose you have to find the limit as xy tends to 0. Xy, sorry, 0, comma 0, that is 0 is 0. Okay, so now if you look at this example, then if you take those two approaches that we had taken earlier, I mean y equal to mx, or I mean x equal to 0, y tending to 0, and x tending to 0, y equal to 0. So then you will see all those three approaches, I mean it is going to give you 0 as the limit. Okay, fine. But the thing is that, yes, thank you. But the thing is that there are only three approaches. Here we have infinite number of approaches, it must give you the same limit. So that is why what we can do, because those three approaches were giving us 0 as the limit. So for this, let us assume that L equal to 0, limit is equal to 0, right? So then, in order to prove that the limit is 0, what you must prove that, I mean, given epsilon greater than 0, you have to prove that there exists data greater than 0 such that this, let me write it down once again so that f of xy minus L less than epsilon whenever this x minus 0 whole square. Sorry, maybe let me stick to x minus a so that I will convert it. Data. So in this particular case, that is what is going to happen. Your 3x squared minus y, x squared plus y squared minus 0 less than epsilon. So whenever your this one 0 square root x squared plus y squared less than 10. Okay, so we have to prove this. We have to prove this a. This part. Okay. So now let us make some observation. See now this one 3x squared y. So this is first. Okay. So now, what is happening? You see that x squared is definitely less than equal to x squared plus y squared, right? Okay?
Yes.
So this implies x squared. So this will be okay, fine. Sorry, I don't need this 3y squared. Okay, so now again you see that your square root y square, it is, I mean, less than equal to square root x square plus y square, right? Okay, and if I look at this, so if I apply this condition whenever this is happening, so this is going to be less than delta, right? Less than delta. If I use this, okay, fine. So now what happens if I choose delta to be equal to epsilon by 3? See, here you have to do a lot of mathematical manipulation. Okay, so that we have to prove that this is strictly less than epsilon whenever this is strictly less than delta. So now if I choose delta to be equal to epsilon by 3, right? If I choose this to be equal to epsilon by 3. So whenever square root x square plus y square is strictly less than epsilon by 3, I am always going to get this to be less than epsilon, isn't it? Fine,
Yes.
fine. So
Fine.
that is why here we have proved from definition that the definition of limit. If I choose L equal to 0, the definition of limit is satisfied. Okay, so that is why your limit xy can be to 0, 0, your 3x square y, x square plus y square, this is equal to 0. This is equal to 0. Okay, so in my next class, I will be doing continuity and partial derivative. Okay, so then we can move a bit faster. Then we can move a bit faster. Okay, so I will leave you with this, and then I will see you in my next class.